The next step we're going to do in our Abaqus series right here is we're going to show you how to make a point mass out of this lump mass right here. So this mass right here adds no structural value. We don't want to look at the failure modes or the stresses on this mass. We're more concerned about our frame here and our cover. So this is a good opportunity to show you how to develop a point mass in Abaqus. So in here, the first step we want to do is we want to go into the assembly module and we want to add our part instances. In this case, our cover and our frame are going to be enough. It's oriented in this global coordinate system right here. Next step we want to do is we want to add the point mass, but before we do that, we have to look at where it's sitting, and we actually have to figure out its center mass and mass moment of inertia and those things. So if we go, I'm going to hide this and turn off this section. And we're going to find out where it's sitting at on this cover. So let's measure this thing. So it's 2 inches in diameter and it is sitting 10 inches from the short edge, 3 inches from the long edge. So if we go into Abaqus, what I'm going to do is I'm going to create an area to attach it to. So if we go into parts, cover, we want to create a partition, a circular partition. So we want to partition a face using a sketch, and we will select the edge, and it's a circle. It's 2 inches. It's a 2-inch diameter, which is 1-inch radius. And I want to measure, put it in the center, 3 inches. And there we have it. And we just middle click and it creates a partition, which is the area it sits on this cover. So now we want to go into Creo, and we want to determine the center of mass and mass moments of inertia. So to do that, we're going to activate the mass, and then go to Analysis, Mass Properties, and we want to select our global coordinate system right here. And the information we need is going to be mass and pounds, our center of gravity in respect to the global coordinate system, which is right here, and then our mass moment of inertia, which has units of pounds, inches squared. And really we just need these diagonal terms. That's all we're going to need. And we can go back into our, you want to create a spreadsheet with point masses, and I just listed the mass part, material, its location, and then its moments of inertia from the global system, its location from the global system, and then you have to put them in terms of Abaqus units, especially your masses. Any time you have mass as a variable in US units, you have to divide by gravity. So these are the units of mass. So that's what we've done here, is we've just taken our mass moments of inertia and divided them by our gravity in inches per second squared. We did the same thing for our mass, as you can see there. And so you'd want to create a spreadsheet like this. This is a good way to do it, to keep things organized. So what we're going to do now is we're going to go into our assembly module, and we're going to create a point that represents our lumped mass. So how do we do that? We actually go into the intersection module, we create a reference point, and we enter our center of mass location right here. So in our spreadsheet, we go back in here, and you can see that I've already have the coordinates right here. Put that in, and you can see we have our point mass in here, and I'll just kind of show you where it's at. So you see here we have our mass location. The center of mass is located there. The next step we want to do is we want to go create a constraint. So we got to tie this reference point to this surface right here that it sits on. So I'm going to create a coupling constraint. So I'm going to call it PM mass, PM meaning point mass. And then we'll have to select our control point, which is going to be our reference point. Give it a name. And then we'll have to select a surface here. It's going to be our partition. And then what side we want it to connect to. In this case, we want to connect to this surface right here, which is brown. And so you have several different coupling constraints in Abaqus, and each has its own application. In our case, kinematic makes sense here because what it does is it'll tie to the nodes on the surface, and those nodes will be displaced with this master node right here, which represents our mass. So we're going to select kinematic. Continuous distributing is applied for fasteners because it allows the nodes to deform a little bit better. The nodes can deform slightly different based on weight factors. In this case, our mass is so stiff compared to this cover. We're just going to select kinematic, and we're going to constrain all degrees of freedom to this node. So anywhere it rotates, moves, these are going to go with it. And we're just going to reference the global coordinate system and tie to the outermost points. That way it'll select points all around the surface. So there we have it. That's our point mass. It's tied to the right location. Next we have to define our inertias. So if we go into inertia, special inertia, create, we want to create a point mass. And we want to assign it to our reference point set, so we can select sets here, RP mass, and then we have to give it a mass right here. And we go back into our spreadsheet, we copy our Abaqus mass, put it in here, and then it also asks for our our mass moments of inertia relative to our global coordinate system, which we got in Creo. And so we'll put these in. We want to put in our Abaqus masses, and I can do that pretty quickly. And I'm just going into detail because some of you guys may want to duplicate this. Step by step. That's the best way to teach. So that's our mass moments of inertia relative to our global coordinate system. We say OK, and when it's highlighted in green, you know you've completed the point mass in Abaqus. So that's all I wanted to show today, and I'll see you next time. Adios.